Looking live at a SpaceX Falcon Heavy rocket sitting on historic Launch Pad 39A at NASA's Kennedy Space Center. In just about half an hour, 4 NASA missions will share a ride to orbit with dozens of other satellites to test new technologies and study space weather. Hello everyone, and welcome to Kennedy for our live launch coverage of the Department of Defense Space Test Program 2. I'm your host, Daryl Nail, with NASA's Office of Communications, and just behind me is the Falcon Heavy rocket on the pad. There was a 3-hour delay earlier due to an issue with some ground support equipment, but that's been checked out and resolved, and now SpaceX is just 28 minutes and 49 seconds away from the most challenging launch in the aerospace company's history. Space Test Program 2 is the first government-contracted Falcon Heavy rocket, and it's managed by the U.S. Air Force Space and Missile Systems Center. The launch will demonstrate the powerful rocket's capabilities for future missions. Of the 24 satellites and countless instruments on board, 4 NASA payloads will benefit future missions to the Moon and Mars: the Green Propellant Infusion Mission, the Deep Space Atomic Clock, the Space Environment Testbeds, and the Enhanced Tandem Beacon Experiment. Each of the NASA technologies has a unique purpose, but they have a common goal. No matter the destination, the NASA payloads on this launch aim to improve future spacecraft design and performance, enabling our bold exploration of space. These NASA technologies will ride on a SpaceX Falcon Heavy rocket, and in about 15 minutes, we will bring you SpaceX's coverage of the launch. But before we do, we want to tell you everything you need to know about the 4 NASA payloads headed to space. And we will begin with a possible alternative to toxic spacecraft fuel. It's called the Green Propellant Infusion Mission. And I'm joined by Jeff Sheehy, Chief Engineer of NASA's Space Technology Mission Directorate. Jeff, thanks for being on the show with us today. Sure. Hey, so this green propellant is an exciting new development technology, but I want to ask you first. You've been with this program since the very beginning, all the way back to the 90s. Sure. When you look back there and you see it on the rocket ready to go, how does that make you feel?
It's an awesome feeling. It's a humbling feeling. There's a little bit of nerves always with any launch, and you think of the launch vehicle carrying the hopes, the dreams, the careers work in some cases of a bunch of principal investigators, a bunch of people who've worked on the technology and developed it to the point where it's ready to fly to space.
And let's take a look at that, because the green propellant we're talking about is actually not green. There's a picture of it, and what's interesting about it is, tell me why that's so amazing that he's able to hold that like that.
Yeah, that's Milt McKay. I was his branch chief at one point when I was at Air Force Research Laboratory. Milt, along with Adam Brand, Tom Hawkins, and Mike Tinnerell, are the principal developers of the propellant. He's in, you can see a lab coat there. He's got gloves on. He's got some goggles. He's not being careless. That's the level of protection you need to handle this so-called green propellant, which doesn't have any vapor toxicity. Hydrazine has tremendous vapor toxicity, and so you have to wear a escape suit to handle that. To load a spacecraft, you have to clear out the whole facility. This can be done in sort of a shirt sleeve environment, as you see there.
Hydrazine is the common spacecraft propellant in use today.
Right.
It would be impossible to do that. This is much more less toxic, I should say, a lot less toxic.
It's a lot less toxic, but it wouldn't be a very good rocket propellant if you sacrifice performance. And so, in addition to the handling and safety considerations with this propellant, it has better fuel efficiency than hydrazine, and it has substantially greater density than hydrazine. So the overall energy density of the propellant is about 50% higher. So I can get 50% more energy in the same size propellant tank, or I can use a smaller propellant tank to get the same amount of energy.
So you can't just develop the propellant, you got to be able to test it in space. Talk about how you're going to do that as we show this animation.
Right, so I brought a couple of little models of this model of the spacecraft, yeah. And this was developed by Ball Aerospace. Ball is the principal company leading this Green Propellant Infusion Mission. You can see the thrusters on the bottom of my little model here, and the solar arrays are deployed here. They'll be stowed for launch. And so we've got the propulsion system, which is developed by Aerojet Rocketdyne. I've got a model of the thruster. This is actual size. The spacecraft there wasn't
small.
Actual size.
Yeah,
It's actually about the size of a dishwasher that you'd have in your house.
Okay.
This is an actual size thruster developed by Aerojet Rocketdyne. So they took the propellant developed by Air Force Research Lab starting back in the 90s and built thrusters that utilize the propellant in the most efficient manner to produce the thrust force that you need to propel the spacecraft. And so we've designed the demonstration so the spacecraft will do all the maneuvers that would be necessary in space, controlling the attitude, pointing in specific directions, changing the orbit of the spacecraft. You can see it there on the monitor. It's being manipulated. That's probably at Ball Aerospace. You can see the size of it in comparison to the person there. The thrusters in this view are on the top.
So it is quite large. And so what alternative fuel advantages are there for future missions to the moon or Mars?
The handling and safety considerations with this fuel being much less than commonly used propellant is a tremendous advantage. The performance increase is a huge advantage. And one thing I haven't mentioned is this propellant is much more cold tolerant than hydrazine. You can let it go to very cold temperatures. It'll warm back up and be just fine. It won't crack your fuel lines or ruin your propellant tank. And so there's a number of mission opportunities that this propellant could satisfy that might not be attainable with.
And last question, briefly, I was surprised how many organizations were involved in this.
Yeah, it was a great partnership, a really excellent example of NASA teaming with private industry. Ball Aerospace, as I said, built the spacecraft. Chris McLean at Ball is the principal investigator. Aerojet Rocketdyne did the propulsion system. 3 NASA centers were involved in characterization work on the propellant and the exhaust from the propellant. And of course, Air Force Research Laboratory not only developed and delivered the propellant, but Paul Zuccarelli there led the team to design all the fueling equipment that would be needed at the payload processing facility.
And all of these people very anxious tonight to watch this launch get off the ground.
Most of the people I mentioned are here and really eager to see this thing go.
Looking forward to it. Jeff Shihai, thank you very much for being here and explaining all this to us.
Great pleasure, thanks.
All right. Moving on now, let's go out to the pad. You can see there, that's where the green propellant is currently loaded right now in its spacecraft atop a Falcon Heavy rocket. We're currently 22 minutes, roughly, before launch, and everything is looking good so far. It's warm weather out here in Florida in this early morning on a Tuesday. Temperatures are in the mid-80s or so. Weather is 80% go at this point, so we're looking good in that regards. Another payload going up tonight is a CubeSat created by students right down the road from us here at the Kennedy Space Center. It's called STANGSat, and it was built by high school students at Florida's Merritt Island High School. Named for the school's mascot, the Mustang, STANGSat purpose is to measure the shock and vibration of a launch to determine how durable CubeSats must be built. And we're wishing them well, as you see the students there. From powering spacecraft to steering them, right now, spacecraft on deep space missions must endure long waits on signals from Earth to know where it is. But as we'll learn in this video from NASA's Jet Propulsion Laboratory, new technology called a deep space atomic clock could one day allow for self-driving spacecraft.
How do we navigate through space? Currently, spacecraft flying beyond Earth don't have a GPS to find their way through space. Navigators on Earth send a signal to the spacecraft, which receives it and sends it back. Extremely precise clocks on the ground, called atomic clocks, measure how long it takes the signal to make this two-way journey. The amount of time tells them how far away the spacecraft is and how fast it's going. The farther out in space the spacecraft is, the longer it takes to receive and send a signal. But what if humans are sent to another planet, like Mars? A two-way system that sends a signal from Earth to a spacecraft, back to Earth, and then to the spacecraft again, would take an average of 40 minutes. Imagine if the GPS on your phone took 40 minutes to calculate your position. You might miss your turn, or be several exits down the highway before it caught up with you. If humans travel to the red planet, it would be better if the system was one-way, allowing the explorers to immediately determine their current position, rather than waiting for that information to come back from Earth. NASA is testing new technology that would allow future explorers to do just that. The Deep Space Atomic Clock is the first demonstration of an atomic clock that can be used for navigation in deep space. It will allow a spacecraft to calculate its own trajectory instead of depending on Earth. If a spacecraft had one of these clocks on board, it could receive a signal from one of those big antennas on Earth and quickly measure its speed and position. The Deep Space Atomic Clock could one day let astronauts navigate safely and accurately to Mars and beyond. This technology demonstration is the first step in making one-way space navigation a reality.
And the Deep Space Atomic Clock is scheduled to launch into space tonight to demonstrate its capability, and this is a full-scale model.
It is a full-scale model, yes.
And this is Jill Soybert, the Deputy Principal Investigator for this demonstration. Thank you for bringing a little show and tell here.
Absolutely.
So what do we have here? I mean, this is, it's not that big for an atomic clock, right?
No, so this is a 3D printed model of our Deep Space Atomic Clock demonstration unit. So this is a model, obviously this one's not going into space tonight, but it is an accurate representation of the size of the unit that we are sending out on the orbital testbed spacecraft tonight.
So how do these atomic clocks help us navigate in deep space?
So atomic clocks keep time, just like any clock keeps time. And navigating a spacecraft throughout deep space is fundamentally a problem of measuring that time. We send a signal from the Earth to the spacecraft and back again. Right now, that's the way we have to operate, because measuring that signal time accurately enough can only be done by these refrigerator-sized atomic clocks that are in the Deep Space Network today. But this clock measures time as accurately and with the same level of stability as those atomic clocks in the Deep Space Network, but as you can see, a much smaller package than something the size of your refrigerator.
Right. Yep.
So something that now we can conceivably put on a spacecraft and launch into space.
Can't put it on my wrist, but you could put it on a spacecraft and this would increase its stability for time and its measurement, where it's going, how it gets there. Will this help us on future missions that we will go to in the, to the moon or Mars?
Absolutely. So this clock technology lets us navigate spacecraft more efficiently and more flexibly. We can use our existing deep space network more efficiently, but it also gives us a really cool application. We can now send a signal direct from the Earth to the spacecraft, collect that signal on board, and then put navigators like me here on the Earth out of work, because the spacecraft can navigate itself. We like to call it self-driving spacecraft or onboard autonomous navigation.
That's fantastic. And there are some benefits to us here on Earth for having this.
Absolutely. So this clock has the stability that's about 50 times better than the onboard clocks on the GPS satellites today, the rubidium and cesium clocks. So you use GPS to find your way here, I'm sure. I did the same thing. I use it every day. If you have a 50-time improvement in the stability of your clock on your GPS satellite, your GPS signal, you will see a better ability to navigate yourself using GPS every day.
Fantastic. And so when this gets up into space, what will you be looking for? How will you communicate to find out if it's working correctly?
So we'll be doing a year-long demonstration experiment. So this is the first time that, well, it's the world's first ion-based atomic clock. So it's the first time this technology has ever been flown. So I'm just excited to turn the thing on. And then we'll run a suite of tests to check out the health and status of the clock. And then we will run an experiment where we collect GPS data that's time-tagged with our clock, and we estimate the orbit and the clock error that's being introduced over time. And we look at the statistics of that to see, how does this clock drift over time relative to a perfect clock? And just to give you a teaser, if it performs the way it does in the ground laboratory, if I turn this clock on today, just let it run, it would take about 10 million years for it to drift off by 1 second.
Incredible accuracy. Even the Swiss would be jealous of. So when this gets out there, will that give better navigation for future astronauts?
Yes, absolutely. In addition to being able to do that self-driving spacecraft thing, which is a critical technology for sending humans to places like Mars, in that scenario, now they can navigate their own ship in real time. They're not waiting for directions to come from the Earth from someone like me. So they can do real-time course corrections that helps them land more safely with less uncertainty in their path. And then once they're on the surface of the moon or Mars, wherever they're going, maybe somewhere even further away, you could use this clock technology to build a GPS-like navigation system at those destinations. So just imagine Having GPS on Mars. It'd be pretty cool.
That'd be fantastic. I wouldn't want to get lost on that planet.
Absolutely not.
Right.
Stakes are high.
Just a few minutes before launch. Are you excited?
Oh, I am so excited. Yes,
bet.
waited a long time for this.
Jill Soybert, thank you for bringing the clock, the model, and for explaining it to us.
Thank you very much, Daryl.
All right, great having you. All right, now we'll go back out to the pad and get another check on the SpaceX Falcon Heavy rocket. As you can see there in the shot, there's 2 pre-flown boosters on either side of this particular Falcon Heavy. It's the first time it will go up into space at night, so we should get quite a show. And we understand that the Stage 2 RP1 load up is complete and closed out. And so things are looking good for this count as we continue on. And now we want to move over to the last 2 experiments and technology demonstrations that we're going to be explaining today. And this is the one that Nikki Fox is joining us here for. Nikki, thank you so much for being here. You are the director of NASA's heliophysics division.
I am, yes.
And you always come dressed for the occasion.
Space Foxes today.
Space Foxes.
Yes, Space Foxes.
After the name. Are you
After the
excited
name.
for this launch?
No, not at all.
Not at all.
Of course, I can't wait. I've been like this all day. So yes, the rocket's right behind us.
Yeah.
We're 13 minutes away. It's just an amazing time.
We've talked about better propellant. We've talked about better navigation, but your experiments aim to give us better protection for spacecraft. Explain how you plan to do that.
That's right. So we have 2 experiments that are flying up today, but one of them is a little technology demonstration. It is 4 small payloads, and they're basically looking at the effect of radiation on technology that we fly every day on spacecraft. And so we're taking them to the most dangerous area that we can get to easily, and of course that's our Van Allen radiation belts. And we're looking at all of so that's of course where spacecraft get damaged, and this poor little one is getting crippled by all the radiation that is hitting it. And that radiation, of course, is some of it's coming from the sun and some of it's coming from outside our solar system. And so each of these little technology payloads is looking at different aspects of that, so we can better plan for spacecraft, better plan for our missions that are going to take our astronauts to the moon, to Mars and beyond, and to make sure that we can mitigate any problems that they would see with that hardware.
And so this technology, how does it absorb what's happening out there, this assault on spacecraft from the sun?
So we're very lucky. We're actually riding along with the Air Force DSX demonstration space experiment. Of course, NASA has the 2 Van Allen probes that have been out working in the radiation belts for about 6.5 years. And so they can tell us what the environment is like. And then these little test beds are going to tell us what the environment is doing to our electronics. It's a beautiful partnership.
Amazing. The 4th payload is the Enhanced Tandem Beacon Experiment. What is that and how does that work?
They are 2 little CubeSats and they are sending beacon tones. So they're basically sending signals out from space down to ground stations here on Earth. And so there is this layer, this sort of twinkling layer that you see there, and that's you have the terrestrial weather forcing up from below, meeting space weather coming down from above. And that atmosphere sometimes gets very disturbed, and it gets like irregularities in it. We call those bubbles. And they can actually corrupt those signals. They can change them. And so we are sending these little beacon tones, and it will tell us a lot about how that atmosphere is interfering with these signals. That has profound effects for us on our ability to do communications and navigation. Just like Jill said, nobody goes anywhere without their GPS. I can't go anywhere without my phone. And so it's really critical for me that GPS is really accurate, so I don't get totally lost. I would be lost without my phone, literally and figuratively.
And these beacons, are they going to be able to figure out where that bubble is formed and then start sending signals through it?
We will send the signals through. We have another mission, Gold, which is taking images basically of those bubbles, and so then we can see how those tones, those beacon tones, are changed by those irregularities in that area. Also a partnership with Cosmic 2, 6 spacecraft that are launching. NOAA is launching those this evening, and they are every now and again lending us 6 little beacon tones to go with our 2 to really give us a full up, robust experiment.
Excellent. And I hear you've got some help from
I
a
do.
University of Michigan student.
I have some students at the University of Michigan. Yes, they helped build the CubeSats. NASA's CubeSat program is an amazing experience for our early career students and new postdocs that can actually get to build technology and put it into space. And so some of those students are actually staying on, and they're going to do the mission ops. They're going to track those spacecraft, bring down the data, and we invite them to help us look at the data also.
What an incredible opportunity for those students.
It's an incredible opportunity for them, and it's a great time to be a heliophysicist.
Nikki Fox, thank you for being here. We appreciate the shirt as well.
Thank you.
Enjoy the launch this evening.
Thank you very much.
All right, time now to turn our focus back to the countdown. Everything looking good. T-minus 9 minutes and 25 seconds and counting. We here at NASA are going to step aside and let SpaceX take you through the rest of the countdown. Jesse and Alex are live from SpaceX headquarters in Hawthorne, California, where their countdown coverage is already underway.
The way we work, SMC 2.0. That means speed, to quickly implement the best solutions to new problems. Partnerships, to forge the relationships necessary for the mutual benefit of the U.S. and our international allies. Innovation, to capitalize on the most advanced cutting-edge technology in the world. Culture, to inspire the necessary risk-taking that will propel us into the future. And enterprise, to share our vision of accelerated and affordable space systems for the Department of Defense. Initially founded in 1954 to develop the first intercontinental ballistic missile, SMC has produced unprecedented and unparalleled national defense space technology for over 60 years. During this time, we've been called upon to support manned space, anti-satellite, and missile defense programs while continuously increasing our space capability. That's where we came from. But a more important question is, where are we going? Humans have always been explorers. We venture to discover that which is unknown. At SMC, we push the boundaries of the known and fight every single day to enhance our technological capabilities, launching past the limits of the sky. We are the pathfinders to the high frontier, and we are building the future of space.
The SpaceX team continues to count down for launch for the nighttime launch of Falcon Heavy. I remember watching the night launch of Saturn V on the Apollo 17 mission in December 1972, and it turned night into day. We're expecting the same tonight from 27 Merlin engines. We're currently at T-minus 7 minutes, 28 seconds and counting. Fuel loading is continuing. We're about to wrap up fuel loading on the 3 first-stage boosters over the next minute. Liquid oxygen loading is continuing. That'll wrap up between 3 and 2 minutes before liftoff on all the stages. We've had the report the last satellite has gone on internal power just a moment ago. Everything's looking good on the satellites. Now, a major activity coming up here in another 2.5 minutes is retract of the strongback. We'll see the clamps open up around the second stage. The strongback will recline about 2 degrees in preparation for launch. We're also just inside T-minus 7 minutes. We've begun chilling in the 27 Merlin 1D engines. Now, a lot's going to happen in the first 4 minutes of flight of the Falcon Heavy. We'll first light the 2 side boosters and then the center core. The flight computer on Falcon Heavy will check the power on all the engines, then command a release from the ground hold downs at T0, so we lift off at T-minus 0. Right after we lift off, we're at full power of over 5.1 million pounds of thrust. 40 seconds into flight, we decrease power on the 2 side boosters in preparation for maximum aerodynamic loads on the vehicle. Once we get through this period, Falcon Heavy will throttle back up to power on the 2 side boosters. We now are 2 minutes into flight, and we're again reducing thrust on the 2 side boosters. This time it's to decrease forces on the rocket structure, especially that structure that holds the side boosters to the center core. The acceleration is building every second as we burn propellant and we're lightening the rocket. So we need to throttle down the side boosters by physically turning off engines to keep the loads below the maximum allowable. 2.5 minutes into flight, we fully turn off the side boosters, called BECO, Booster Engine Cutoff. Then we'll use high-pressure gas separation system that's mounted on the top and bottom of the center core. That'll unlock the 2 side boosters and push them away. Now, once we're clear of the side boosters, the center core will throttle up to full power and burn another minute. Finally, at just past 3.5 minutes after liftoff, the center core shuts down, main engine cut off, and the second stage separates. Now from this point on, it's like a Falcon 9 mission, other than we do happen to have 3 first stage rockets returning to Earth at both Cape Canaveral and the drone ship. Meanwhile, on the way into orbit, the fairing will separate, the second stage engine will undergo a series of 4 burns, eventually delivering all 24 satellites to their intended orbits. Now it's a demanding sequence of events for the Falcon Heavy tonight. But from this point on, everything is looking good. We're at 4.5 minutes. We're getting ready to recline the strongback. So let's watch and listen to the final countdown.
Strongback starting to retract. And negative Y LOX load is closed out. And positive Y LOX load is closed out. Strongback lower is closed out. And stage 1 LOX load is closed out. And vehicles on internal power. And stage 2 LOX load is closed out.
Ground gas close is complete.
And the vehicle is in startup.
This is the mission director. Go for launch.
T-minus 30 seconds. T-minus 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Ignition.
Vehicles pitching downrange.
T plus 25 seconds into flight under the thrust of over 5 million pounds. Falcon Heavy is headed to space. We're getting ready to throttle down for passing through the period of maximum dynamic pressure. We've heard call out of throttle bucket for side core. We're through max Q.
Vehicle is supersonic.
Everything continuing to look good on the Merlin 1D engines. We're throttling back up on the side boosters to full power. A minute 15 seconds into flight. Performance looks nominal. Currently, the next event coming up in about 2 minutes. We'll hear call out of chill-in of the MVAC-D engine. That allows liquid oxygen to the top of the turbo pump to get the second stage engine ready to chill for ignition in just a couple of minutes. We're 2 minutes into flight. We've begun to decrease thrust on the side boosters to minimize acceleration and loads on the Falcon Heavy structure. We've turned off one engine on each of the side boosters to decrease that load. Now our next major event coming up here in about 10 seconds, shutdown and separation of the side boosters. The view should be the side booster cameras on 2 sides and the center core in the middle.
Booster shutdown.
Booster separation confirmed.
Over the cheering in the background, it's going on midnight, but a lot of people here at SpaceX, side boosters have separated. They're getting ready for their burn back to Cape Canaveral. You can see on the left and right views, the side boosters have ignited. The center core continues under full power. Everything looking good on the Falcon Heavy. Next event coming up in about 15 seconds will be shutdown of the center core, followed by stage separation and ignition of the second stage engine. Good views of the 2 side boosters under the thrust of 3 engines each, slowing down their velocity and coming back towards Cape Canaveral. We have shutdown on the center core.
Stage separation confirmed.
We have successful separation and ignition. We're coming up on shutdown of the 2 side boosters.
Side booster, boost back shutdown.
And we've heard the call out side booster, boost back shutdown. The center core, you can see, is not doing a boost back. It's headed downrange to the drone ship. Here comes fairing separation.
Cross-ranger nominal. Fairing separation confirmed.
We have confirmation of the payload fairing separation. So far, 4 minutes, 17 seconds into flight. Second stage looking good, headed to low Earth orbit, carrying the 24 satellites. The side boosters have done their first boon, coming back to Cape Canaveral. The center core has separated and is beginning its long coast downrange to the drone ship in the Atlantic Ocean. So at 4 minutes, 35 seconds and counting, everything looking good on Falcon Heavy.
Now those side boosters are making their way back. Their grid fins on all 3 boosters should be deployed, and those are help guiding them to their landing zones. As a reminder, today we will be attempting to recover all 3 of these first stages, and all 3 boosters are currently making their way home. In just a few minutes, the side boosters will execute an entry burn followed by a landing burn, and the center core will complete the same burns just a few minutes later. Both burns are used to slow the stage's speed down rapidly before landing.
At the time of separation, the side boosters were traveling slow enough to turn around and make their way back to land at our side-by-side landing pads. The center core is going too fast to efficiently return to the Cape, so we're using our autonomous drone ship, Of Course I Still Love You, as we mentioned earlier. As a reminder, our drone ship is positioned twice as far offshore than normal, so we may not get visuals of landing tonight. Also coming up in a few minutes will be the call out for second engine cutoff. So coming up in about a minute here, we're going to look for that side booster reentry burn to begin. Shortly after that, that should end about 20 seconds later. You can see both of those boosters on the infrared camera on the left side of your screen. Again, about 30 seconds until we expect those side boosters entry burn to begin. So keep an eye on the left side of your screen. In about 10 seconds, we should see those side boosters reignite for their entry burn.
Side booster entry burn startup.
And we have confirmation that the entry burn has begun. And in about 15 seconds from now, we expect that to end. Oh, wow. You hear the crowd cheer behind me. And that entry burn has completed. Note that second engine cutoff and the center core will be landing almost at the same time. So we're going to have a few events in succession at about T plus 8 minutes and 21 seconds.
Both side booster FTS is safed. Stage 2 FTS is safe. And terminal guidance.
In about 20 seconds, we're going to look for that side booster landing burn to begin on both boosters.
Side boosters transonic.
About 10 seconds away.
Side booster landing burn startup.
We've heard the call out for side booster landing burn startup, and there you see it on your screen. See it coming towards our 2 landing pads. See those landing legs deployed. Incredible.
Side boosters are successfully landed.
Confirmed side booster landing. What an iconic view. We've also at the same time, I believe we've had second engine cutoff at the same time. As we mentioned earlier, the center core entry and landing is going to be risky. During entry, it'll face more heating and dynamic pressure than we've ever experienced on Falcon 9 or Heavy flight before. Why, you ask? Because we have to lift the second stage higher and faster than other Falcon Heavy flights in order to have enough performance in it to execute 4 burns into all the different orbits. So coming up at T plus 9 minutes and 39 seconds, we should see the center core entry burn ending.
Center core entry burn.
Oh, we have the confirmation. Looks like that was the confirmation for it to begin. So we're a little bit off the timeline.
Center core entry burn shut down.
And we had just heard the confirmation that center core entry burn has shut down. And now that the entry burn is complete, the center core is moving back about 20% faster than it was at the end of the Falcon Heavy 2 Arabsat entry burn.
First stage KPL expected.
Now we're coming up, we're just about a minute away from that center core landing burn beginning, and as we've been mentioning, this will be the most difficult landing that we've had to date. This will be a 3-engine burn. That center engine will start up first, and then 2 outer engines will start up as well for that landing burn. Now we're just 30 seconds away from that center core landing. And it's no surprise that we do not have a live view of that center core as it's coming down, but it looks like we got a live view of the drone ship there. Of course, I Still Love You. If you're just now tuning in, we're just about 10 seconds away from that center core landing burn beginning.
Stage 1 landing burn has started.
And we have confirmation that the center core landing burn has begun. You could see that coming down on Of Course I Still Love You. Got a pretty good view. And as you can see on our screen, it looks like our center core did not make it on our drone ship, Of Course I Still Love You tonight. Again, as we've been mentioning, this was the most challenging landing that we've had to date, and this is our secondary mission. So our primary mission, we just heard the call out for a good orbit of our second stage. So we are actually just moments away from our first deployment of the evening for Oculus ASR, which was developed by students at Michigan Technological University. We will be passing beyond the Bermuda ground station, so there is a chance that telemetry may cut out a few seconds before deployment, in which case we won't be able to see the satellite actually deploy on camera or get confirmation of a successful deployment until telemetry is restored. Now we're just about 30 seconds away from that deployment, so we'll listen into the nets for that confirmation. Looks like we still have that live view. Might have a chance to see this deployment live on camera. Again, we are waiting for the Oculus satellite deployment. And as we expected, looks like we lost that live view. So we will wait to get some confirmation of that deployment, and we will update you guys in a few minutes later on in the webcast. We are now in between ground stations for the next few minutes with nothing to see. So we are going to take a quick break, but we will be leaving you with an animation that shows you where we are throughout the coast phase. We will be back around T+20 minutes for our next set of deployments. And it's worth noting that since we won't acquire ground station coverage again until T+21 minutes, we are going to miss that first P-Pod 1 CubeSat deployment. See you back here in about 6 minutes.
A great job by our friends there at SpaceX covering the launch of the Falcon Heavy as it lit up the night sky for the first time here on the Florida Space Coast. And of course, watching the boosters come back was just as impressive here live at the Kennedy Space Center. There were some big booms that were heard, and wow, it was impressive. Now, the work is not done. The NASA missions and their host satellites will deploy over the course of the next 3 hours. The SpaceX team will stay live until the final satellite deploys. Now, for NASA-related deployment and other post-launch updates, visit www.nasa.gov/SpaceX and follow along on our social media channels. We hope you enjoyed our coverage of the launch of a Falcon Heavy from Florida Space Coast. I'm Daryl Nail, and for all of us here at NASA and the Kennedy Space Center, have a good night and keep looking up.